And I think one of the most promising ventures is the ability to combine kind of the best of both worlds of these systems.
Graduate school presented Christian Spallone with a unique opportunity, mix together his fascination of forecasting with his programming prowess.
So Christian was an undergraduate student at Penn State, and he took an AI course in meteorology. And through that, we found we both had an interest in seeing how we could use artificial intelligence to better predict the weather.
As I started to look into researching different graduate programs, I knew more about the different role and the increasingly important role that AI was playing within the atmospheric sciences. But because it was so new, there was still a lot of uncertainty about it.
As Christian's research project came together, it became clear he would need to combine evaluation with creation to explore artificial intelligence methods for weather prediction. It all started with understanding how AI models work.
In terms of a simple explanation, we can kind of describe the way that AI models make a prediction by essentially looking back at all of the previous data that we know about the weather. And so based on, say, 40 years of past weather information, if we can teach a model to learn all the different patterns in all of these different years and these different variables that exist through these reanalysis data sets, right, that reconstruct that history, if we simply teach a model those relationships, we can allow it to be trained on that data. And then as we apply it into the future, we can allow it to make predictions using some sort of just initial state of the atmosphere.
While these AI models can describe how the atmosphere will evolve with time, they are fundamentally different from the traditional models you're used to seeing on Weather World.
All of our traditional models utilize those initial conditions to make a prediction, but they do it by using all these physics-based equations, right? So really complicated numerical systems that take a really long time to run, but may be very accurate. So what the AI model is doing is cutting out all of that interchange with these equations that take a while to run, and simply using that initial state and then connecting it to past patterns that it's been trained on in order to extrapolate that, say, 10 days into the future, right? And so that's able to make a prediction in a much more efficient time frame, and sometimes a more accurate prediction as well.
The first part of Christian's research focused on the accuracy of these different AI systems for specific types of high-impact weather, like winter storms.
And once I had a lot of these high-impact winter events that were actually selected for a database, I can go about kind of analyzing the accuracy of these different models. So in order to do that, we have to find some sort of actual ground truth data that represents what actually occurred in these different storms. We usually use reanalysis data for that specific circumstance. And then we can compare different forecasts from different modeling systems. So these are things like the European model or the American GFS model, two different AI-based models. So we can take a collection of these different systems and we can use those to see how accurate they are in predicting that specific reanalysis data set, for example. And then that tells us how accurate they were in predicting that specific storm case.
Sticking with high-impact weather, the second part of Christian's research involved thunderstorm forecasting. But instead of evaluating existing AI models for accuracy, Christian created his own.
We had to process a lot of different satellite information, radar data, in order to teach a model to predict these specific storm cases in real time. And then this involved a lot of training of the different systems, which is a complicated task. We were able to train for convection this system in only a matter of a couple hours, which is really great. So some models that are more advanced and more complicated, like a lot of the global models that may use like 40 years of data, some of those tend to take on a magnitude of days or even weeks to be able to train using GPUs. We could run this model that we've developed in under a second, which is able to produce pretty accurate predictions and then rapidly update those on a real-time basis.
Combining both parts of his research project, Christian was able to prove just how useful AI models can be.
We were able to show how a prediction system like this might be practically used someday for making decisions, for example, at a big sporting event, whether to take action as a thunderstorm might approach. So it was great to see the practical applications of the research that we developed together.
The big question is, how will these AI tools change the way we forecast weather?
So that's, of course, the million-dollar question, right? And I think we have the traditional models, which are really good at getting all of these physics right in the systems. And then we have these AI models that are very efficient and also have all of this past information embedded within them because they've been trained on it, right? And so if you can somehow take all the good pieces of both of those and merge them together into some sort of hybrid system, that could be really powerful. And I think that's really the way forward in terms of the next 5 to 10 years in this field.
While Christian was working on his graduate degree, digging through data and making forecast models of his own, he also continued to be a forecaster on WeatherWorld.
This is the first time I've worked with a graduate student that has also been involved with WeatherWorld. And it's a great opportunity for our students to be involved with the day-to-day weather, as well as to increase their ability to effectively communicate the research to a variety of audiences.
It's hard to understate how much WeatherWorld has helped me. I think just from a presentation standpoint, looking back at like the early days of my undergraduate experience to thinking about now, like the way I've communicated information has like completely changed. And I'm sure some of that's driven by having more practice actually communicating scientific information. But on WeatherWorld, that's what I'm doing essentially every time I go on air, right? And so I'm getting experience with that through that process. And so it's helped me so much by being confident in a lot of the things I'm saying.
With a master's degree in meteorology and atmospheric science now in hand, Christian is embarking on a new chapter, once again looking to combine his experiences with research, forecasting, and communications.
It's been great to watch Christian grow in his ability to be an independent researcher, whether it's developing AI code, writing scientific papers, presenting and developing and testing his own research ideas.
I'd like to apply a lot of this knowledge that I've gained kind of not only in artificial intelligence, but really within this applied space of meteorology, somewhere into the private sector.
And he'll do just that, working behind the scenes with the innovative folks at the Weather Channel. For WeatherWorld, I'm Rob Leidick.